Now, we haven't proven that yet, but that's our intuition. That's our sneaking suspicion. Now, let me show you what I meant by why I use hit and miss or hit and not hit rather than success and failure. Okay? Because a problem can be written as follows, and it can be really, really confusing. Whoops, don't do that. It can be really, really confusing. I'll show you what I mean. Excuse me. All right. So let's say that for any given cancer screening, the probability that I have cancer, all right, on a certain cancer screening particular to men, all right, a blood test, the probability that I have cancer is, let's say, 1% or 0.01. All right, so the probability of not, this little tilde means not, I'm going to interchange that with the bar, of not having cancer is equal to 0.99. Okay, now let's say that we take 100 men. So we got 100 men. Now hopefully your brain's clicking. Oh wait, 100 men, that's the number of trials, that's our sample size. So n equals 100, p equals 0.0. Whoa, let's not write that up yet. Let's take our time and make sure we define this right. I want to find the probability that exactly 95, write this down, the probability that 95 men don't have cancer, or at least test positive for cancer, don't have cancer. All right? Now, so not having cancer is now considered a success if it were, right? Do you see what I'm saying? In other words, this is a hit, and this is a miss. Okay? Even though you may think that the probability of having cancer is going to be your P, and your probability of not having cancer is going to be your Q, it's all contextual. 95, I'm finding the probability that 95 men don't have cancer. So I know if n is 100, I know x equals 95. I know that P, which is my success, which means doesn't have cancer, which is a failure as far as testing for cancer is concerned, is 0.99. And I know that Q is 0.01. The moral of the story is take a deep breath and figure out exactly what a hit is. Don't figure out what a success or failure is, because you can get really screwed up with that. So let's just write it up, and then we can do it on our calculators when we get back to class. So the probability that x equals 95 is equal to 100, choose 95, times success is 0.99 raised to the 95th times 0.01, excuse me, raised to the 5th. All right, and then it becomes a calculator problem. You can do it on your computer, you can do it on your calculator, you can do it all over the place. Okay, things like that. All right. So we now have the binomial probability formula. Life is good. Hopefully we've made a little sense of it. Okay? All right, now we're going to take this information, we're going to change it up a little bit, make it easier for us. And we're going to actually show that this is a probability distribution. Remember back in the day when we said probability distributions, you've got outcomes, you've got associated probabilities, and then we could find means, variances, and standard deviations. So let's go back to our Big Mac problem, okay, because I'm going to keep it super simple. Again, probability of a Big Mac is 0.7, Q was 0.3. All right, now check this out. Remember, we need an X, we need an N, which is number of trials. We need an X, which is hits, number of hits, I guess. We need a P, which is the probability of a hit, and Q, which is the probability of not hit, or probability of a miss. Same thing. Okay. Now, watch. Let's change the problem up quite a bit. Instead of our 10 cars, because that'd just be a pain in the butt, let's let n equal 4. Okay? So everything's still the same as it was before, except n is going to equal 4. And I'm going to let x float. Okay? So I'm going to show you how the binomial probability distribution is actually a probability distribution. All right? Rather than figuring out exactly the number of cars that ordered a Big Mac, we're going to figure out the probabilities of all of them. Okay, so we're going to start with 0, and 1, and 2, and 3. I probably should have made this bigger, but that's okay. Now, I'm going to just come kind of splaying out here real quick. All right, remember, n is 4. I'm looking for really what this value right here is, the probability that x equals 0, which is going to be 4 choose 0, 0.7 to the 0, and 0.3 to the 4th. You see how, remember how that works out? This is x is the number of hits, which is the number of Big Macs that were ordered. Okay, so I'm going to throw in my fancy schmancy calculator here. Give me just a second. I've got, let's see, 4 choose 0, which I know is 1, but it'll be easier for me down the road. So what do we say? 0.7 to the 0 and 0.3 to the 4. And I end up with 0.0081. Sorry about my small writing. All right, this guy right here is the probability that x equals 1, which is 4 choose 1, 0.7 to the 1, 0.3 cubed, etc. Okay, so if I hit second entry on my dangle here, and I go 4 choose 1, 0.7 to the 1, 0.3 to the 3rd, I end up with 0.0756, etc. And I'm just going to blow these things through my calculator real quick. 4 choose 2, 0.7 squared, 0.3 squared, and I end up with 0.2646. And look at these are going to grow all the way throughout. As I work my way through these problems, I know that they're going to grow because I know that if I had 10 trials, at 7 is the maximum number, but I've only got 4, so we're just going to watch these things grow throughout. Let's see, 0.3 to the 1. This guy's 0.44116. And then last but not least, let's see, remember 4 choose 4 is easy because it's just there's only one way to choose 4 things from 4. And I get 0, and this is 0.2401. Look where the biggest is. If you think about it, when we had 10 trials, we knew the biggest probability was at exactly 7. When I have 4 trials, it's like that thing scales down. Now, I'm going to add all these up. If I go the sum, remember for a binomial distribution, or excuse me, for a probability distribution, we know the sum of the probabilities has to be 1. If I go 0.0081 plus 0.0756 plus 0.2646, assuming I'm plugging these things in right, which is about 50-50. There's a binomial distribution right there, right? Plus 0.2401 plus 0.2401, and voila, 1. Now, hopefully you also remember that mu is equal to, in these guys, it's the sum of x times p of x. In other words, if I did this times this plus this times this plus this, etc., I would get the mean, and that the variance, remember this thing was the god-awful one, the variance, not the standard deviation, is equal to the sum of x squared times p of x, right? And that was the sum of those guys, and then you subtract out mu squared. And then, of course, sigma is just the square root of sigma. Sorry, try that again. The standard deviation is just the square root of this guy, so stick him in there. The problem is, like in this guy, if I'm going to try and figure out what the mean and the standard deviation, the variance and the standard deviation of these guys are, for me to be able to do this mathematics, I would have to build one of these, a probability distribution. Well, I'd have to, I mean, look at this. I got n is 100. It would be god-awful. I mean, even with computing the way it is today, we'd have to know how to program it. Guys, there's a much simpler way to do that. Now, I am going to give you these as formulas. And like all other formulas, I'm going to give you note cards. You guys are going to be able to use note cards for your formulas, okay? I'm not expecting that in a 3-week course you're going to be able to memorize all the formulas. Heck, if it was a 16-week course, I probably wouldn't expect you to memorize all your formulas. However, we're not going to prove this guy. I might throw it in there as a project. You never can tell because it's actually a pretty cool little proof, but it requires a little bit more mathematics than we're really prepared for right now. Watch how easy this is. Notice, without me having to do any of this stuff, which is very useful and very helpful in terms of seeing that a binomial distribution is actually a probability distribution, but watch how simple this gets. This is for binomial probability distributions, so sometimes you'll see this as PD only. I want you to triple underline that in your notes if you're making notes. It's only for binomial distributions. All right, for just regular old rank and file garden variety probability distributions, you have to go through this problem, through this process right here to figure out the mean, the variance, and the standard deviation. But watch this. Here it comes. Oh, n times p. That's pretty easy. The standard, the variance. You ready for this one? N times p times q, and the standard deviation is the square root of n times p times q. That's it. That's all that you have to do. So for this guy, watch. All I have to do is take n, which is 100, and I have to multiply it. Now, wait. Look, now remember what a hit was. That's this guy. So we're talking about the average number of patients that won't have cancer within the context of that problem. Just be really careful. You guys are going to drive me crazy. Now, you probably will be able to tell if the probability of getting or of not having cancer is 99% and there are 100 people, we can expect that 99 out of those 100 on average aren't going to have cancer. The variance is 100 times 0.99 times 0.01, which in this case is 0.99, right? 99 times 0.01. Now, that's completely coinkydink. That's totally coincidental that it worked out the way that it did. Maybe I could pick better numbers when I do it in the future, but it is what it is. All right? And then, of course, standard deviation is just the square root of all that. So the square root of 0.99 is, can't do that one in my head, 0.99. It's pretty close to 1, but it's not, is 0.995. Right? So if I wanted to know what the mean, the variance, and the standard deviation of this guy right here is, given, now remember, these can't change. So this is specific only to the distribution, the probability distribution that is created by this setting. It's not, it doesn't have anything to do with my Big Mac problem. It only has to do with my problem where I got 100 guys, I give them 100 different blood tests, and then I look at how many of them end up without cancer. This is what I get. Okay? Now, remember, mean, variance, standard deviation, brick and mortar, man. It's very important that we know how to find these means and standard deviations in particular, although variance is very important as well. All right. Hey, that's the end of Chapter 5. I hope you enjoyed it. We're going to revisit the binomial distribution down the road, but for now we're done with binomials. I always really enjoyed this section, so I hope you did too. All right. We'll see you in class.